Hi, today we are going to discuss about interpolation method using polynomial. So this is the introduction. This is the data of average tuition and fee for 4-year private college. So this is the data. Academic year ending in 1973. And the tuition fee is this. You can ignore this part. So I have the data such as in 1973 the tuition fee is 1,800. In 1978 I have 2,700 and so on. So the question is, can we approximate the average tuition fee when the academic year ended in, let's say, in 1975? That is not in the table. So I have the 1973 here, 1978 here. What about in 1975? Can I approximate the tuition fee based on this data that I have? So a more advanced question will be, can we see the data here as a function in time? So we can approximate average tuition and fee at any time you want. So this problem is usually known as interpolation problem. But remember, this is not an extrapolation problem. What I mean by extrapolation problem is I have the data is until 2003 and I want to know the future of 2000 after 2003, that is maybe 2020 maybe. So that what you usually call in extrapolation, predicting. But this is interpolation based on the data that we have. And the answer for the question above is yes. Okay, then let's see how many points needed to make a data a function. Now let's say we have only 2 points. Can we make a function from 2 point? What function? This means we want to find a function that have that fits to 2 points. And I can look as like this. Let's say that I have a table as follows. X equals fx when x equals 2. When x equals 2, the y equals 5. When x equals 5, the y equals 10. So I have two data, 2, 5, 2, 5, x, fx, x, y, and 5, 10, 5, 10. So we want to know what is fx when x equals 4. This is not in the table, but I want to know. Find an approximation of fx when x equals 4. That is, I want to find what is f4. So I want to use polynomial to approximate f4. So I have I remember at the junior high, if I have 2 points, I can make a line. So I can use polynomial approximation such as fx equals a line. b0 plus b1 times x. That is a linear. So then I have f2 equals 5 and f5 equals 10. And fx is given by b0 plus b1x. And I can substitute f2 equals 5. If I substitute f2 equals 5, I have 5 equals b0 plus 2b1. And I can substitute f5 equals 10. So I have f5 equals b0 plus 5b1. So I have 10 equals b0 plus 5b1. So here we have to solve 5 equals b0 plus 2b1 and 10 equals b0 plus 5b1. So in order to solve that, I just use the Cramer rule. I have b0 equals 5 over 3 and b1 equals 5 over 3. So then I have the polynomial that I want to have. That is a linear one, an equation of the line, y equals 5 over 3 plus 5 over 3x. So at f4, I can approximate the value should be 25 over 3. Okay, yeah? But what about if I have 3 points? In junior high, I remember also, if I have 3 points, maybe this one, 2, 5, 5, 10, and 1, 3, I have 3 data. the same. I want to approximate fx at x equals 4. What is f4? I can use a quadratic equation, that is fx equals b0 plus b1 times x plus b2 times x squared. And I can do the same game as before, and we will get what we have in the slide on page 4. But it's very cumbersome. Why? Because we in the Cramer rule, so we have something like b0 times something like b1 time plus something times b2. So I have 3 variable and 3 equation. So I have to solve 3 equation and 3 variable. And by Cramer rule, I have to solve 3 times 3 matrix, determinant of 3 times 3 matrix, divided by determinant of 3 times 3 matrix is very cumbersome. And so I have fx, f4 just as in page number 4 that we were going to discuss. And if I have 4 points, I can approximate with a cubic equation. Yeah. I can do the same game, and we will get what in the slide. We will have what in the slide page 4. So if we have only n points, what kind of function can we make in general? This is a polynomial of order of degree n minus 1. Okay, yeah. For 3, quadratic. For 4, cubic. For n minus 1 degree polynomial. In this course, we are going to discuss 2 methods for interpolating polynomial, that is Newton's divided difference method and Lagrange method. So the first one, I am given this data 1, 3, 2, 5, 5, 10, 6, 11. So because 4 is between 2 and 5, 4 is between 2 and 5. So if I want to find the first order Newton's method, I can use using 2, 5 and 5, 10. Okay. So this one I got from this. This one I got from this. 5 over 3 plus 5 over 3x, this one. And you can do the same for the third, for additional 1, 3, the same as this. Additional 1, 3 data. I can use fx equals this, and you can find b0, b1, b2, and you will end up with this. And if given 4 information, this one, 2, 5, 5, 10, 1, 3, and 6, 11, additional 1 point, you can find an approximation of f at x equals 4 also by considering fx equals a cubic equation. And you can have this one. What we can see that the constant change 5 over 3 for 2 information, 125 divided by 11 for an additional information, 3 information for 3 data. And for 4 data, I have 1. And we can look at the coefficient of x. It changes also. And the coefficient of x squared, it changes also. So this is not convenient. Why? Because the coefficient always change. And it is not so convenient. Because if I have n data, I have to repeat all of the computation and find an equation and find n coefficient, and very cumbersome. So Newton's divided difference want to improve that method so that the the coefficient that we have found is still the same. So let's say we want to find f4 using 2,5 and 5,10. Then what we usually do, we make a table such as this. This is the 0, 1, x0, 2, x1, 5, f at x0, 5, f at x1, that is 10. So I can find the first difference. What is the first difference? 10 minus 5 divided by 5 minus 2. So that's what we usually call the Newton's divided difference. 10 minus 5 divided by 5 minus 2. So this will give you 5 over 3. So the polynomial interpolation function is b0 plus b1 times x minus x0. So b0 should always be this one. This one is b0 and this one is b1. So you have 5 plus 5 over 3 x minus 2. 2 is x0. x0 is 2. Okay, so f14 is 25 over 3. This is the same as what we do here manually. The same. 5 over 3 and f4 is the same. So I can look for the second order. For the second order, I have an additional point and I can find the difference. What is the first difference for this one? For these two rows, that is 10 minus 5, 10 minus 5 divided 5 minus 2. So I have the same difference as before. And what about the first difference in the 2 and third row? The second and third row. So I have 3 minus 10 divided 1 minus 5. 3 minus 10 divided by 1 minus 5. That is 7 over 4. But I have this and x here, so I can find the second difference. The second difference is 7 over 4 minus 5 over 3 divided by, what is the x here? I can just look at this. X is 1 minus x is 2. So 1 minus 2. Second difference, 1 minus 2. 7 over 4 minus 5 over 3 divided by 1 minus 2. That is minus 1 over 12. So this is b0, this is b1, and this is b2. So the interpolating polynomial second order Newton method will give you f2 to correspond to second order interpolating polynomial equals, this is the formula, b0 5 plus b1 5 over 3 times x minus x0, x0 is just 2, plus b2, b2 is minus 1 over 12, times x minus x0, x minus x1. x0 is 2, x1 is 5. So I have this as our second order Newton's divided difference interpolating polynomial. And at 4, I can substitute. So this is the second iteration, the second order of Newton's method. And I can look at the third order also if I have an additional information, that is 6,11. So I can find the first difference between first row and second row. This one, first difference for the second and third row. And this is the last one, is the first difference between the third and the fourth row. So I have first difference. And I can have the second difference. What is second difference? The second difference is between this and this. 7 over 4 minus 5 over 3 divided by 1 minus 2. And what about this? The second difference. This one minus this one divided the second difference. 6 minus 5. This is 6. This is 5. So 6 minus 5. What about the third difference? I can look at the third difference. minus 3 over 20 minus 1 over 12, that is plus, divided by third order difference, 6 minus 2. 6 minus 2, that is minus 1 over 60. So the interpolating polynomial will be 5. This is b0. This is b1. This is b2. And this is b3. So I have b0, b1, b2, b3. And it is multiplied by x minus x0, that is x0, 2. X minus x0, x minus x1, that is 5, x minus x1. X minus x2, that is 6. So I can plug in all, and I can the third order Newton's interpolating polynomial. And I can have the approximation is this. So it should get better and better. Okay. And now we are going to talk about the last method, that is Lagrange's method. So we are given the same set of data, and we want to determine F4. So first of all, we are going to use two data. For if I have two data, I can just have a linear. So how can I make the Lagrange interpolating polynomial? So I let fx equals a fraction times 5 plus a fraction times 10. So this fraction corresponds to the data 2, 5, and this term corresponds to the data 5, 10. Once again, this term corresponds to data 2, 5, and this term corresponds to the data 5, 10. Because this term just correspond to comma 5, I don't want this term correspond to this data. So when I put x equals 5, I want to have, when x equals 5, I want this data should be, this term should be 0. So I put x minus 5. Why? Because in this term, I just want to correspond to this data. So if I substitute x equal 5, I want this term vanish. So I put x minus 5. The same for this term. This corresponds to this point. So I don't want to correspond to this point. So when x equals 2, I want this to disappear. So I put x minus 2. But if I put, remember, this is the term that corresponds to 2, 5, and this is the term that corresponds to 5, 10. But in this term, if I put 2 here, x equals 2, I have 2 minus 5. So I should divide it by 2 minus 5. Why? Because if I have x equals 2, I have 2 minus 5 divided by 2 minus 5, and this cancels out, so I have just 1 times 5. And if I substitute 2 here, this will become 0, because this doesn't correspond to this data. So the Lagrange interpolating polynomial should be this one. And this one also, yeah. When I substitute 5 here, I have 5 minus 2. So it to become cancel out, so I have divided by 5 minus 2. So F14 is 25 over 3. This is the same as this one. The first order Newton's divided difference. Okay, yeah. And now let's look at the first order Lagrange method. The second order Lagrange method. So fx equals this one. This term should correspond to this point. This term should correspond to this point. And this term should correspond to this point. So in order this one just correspond to this point and not the other point. So at this term, we have to include x minus 5 and x minus 1. X minus 5 and x minus 1. Why? Because if I put 5 and 1, here it will become 0. Because I just want to have this correspond to this point, just this point. And this one, I want to have this just correspond to 5, 10. So I want I want to eliminate if x equals 2 and x equals 1. So I put minus 2 and x minus 1. So it will disappear if I have x equals 2 and x equals 1. Okay. And this corresponds to this. So this just correspond to this. So when I substitute x equals 2 and x equals 5, it should be 0. So I have to have x minus 2 and x minus 5. So this will become 0 if I put this x equals 2 and x equals 5. Because I want this term just correspond to this and not this. Okay. But if I put 2 comma 5 here, I have 2 minus 5 times 2 minus 1. So to cancel it out, I have to divide it by 2 minus 5 divided 2 minus 1. The same applies here and the same applies here. So I have this as our second order in Lagrange interpolating polynomial. And this is the approximation 17/2. This is the same as the Newton's method 17/2. Okay, yeah? And we can look at the third order, the same technique as before. You can try it on your own. Now we are going to talk about the error in interpolating method. So just as error for finding roots, when we are using numerical methods for finding roots, there will always be an error. So we classify into two error, that is exact error from the exact value, and relative error from the previous iteration of approximation. In general, we didn't know the exact error, because we didn't know the exact value. We don't know the exact value. So we will be using relative error more useful. Let's look at the error for Newton's method. So we are given by this. This is the first order approximation of Newton's method. I have 25/3. So the error of this approximation, if I have an additional information, that is 1/3. But for an additional information 1/3, I can find the second order Newton's method, that is 17/2. So the error is given by the difference between f2 and f1 at 4. That is this term, because this term still remains. Okay, so the relative error for the first order approximation. First order, what is the relative error of this? Just the second order minus the first order. And what about the error for the second order Newton's method? So I have to have an additional information, that is 6,11. So this should be 3, sorry. This should be 3. F3, the third order approximation, is 43 divided by 5. And you have this additional term. So the error is this additional term. That is the absolute value of this, that is 10%. Okay, yeah? And for the error for Lagrange method, yeah, the same as Newton. Yeah, you can figure it out yourself. And from last week, finding roots, we are going to use this book, Numerical Methods for Engineer, by Stephen Chapra. Okay, I think that's all. Thank you.